we realize that this doesn't have a lot of types of geometry that you might be interested in modeling, like through holes and freeform surfaces. So if you're interested in seeing more complex or just different examples, just ask us. We want to hear from you. We can set up a private web meeting or meet in person, and we'll show you something that applies more closely to your specific application. So we're going to go over two basic types of reverse engineering. One's designing around objects. So, maybe a chassis you're making a body kit for, or some other aftermarket accessory, an engine room or a compartment that you need to retrofit something into, or maybe you need to design a tool or an assembly fixture like this one here around some component that comes from a supplier or a customer, and they won't share the CAD files with you. So, we have the common example of designing around other objects, and then we have copying objects. So, maybe an old car part or a boat propeller that was made in times before CAD, or made by a supplier that shut down their operations. You can't get it anymore. You might want to copy something exactly, or you might just want to use it as a starting point and then make modifications that improve it or adapt it to some new system. So we'll try to show you examples of both. There are also two basic flavors of models that can be produced that we'll be touching on, and the first is a parametric or feature-based solid model. So I imagine most people in this room are SolidWorks users. You're probably all familiar with this type of modeling. If you want to change dimensions on the final model, or if you need a model that doesn't necessarily conform perfectly to the scan, but instead reflects the intent of the designer rather than the imperfect reality of the manufacturing process, then this is the way we need to do it. So we'll be creating a model using, most of the same commands you'd find in SolidWorks or other CADs, but the difference here is that a dedicated reverse engineering program like Geomagic has a bunch of additional specialized features that allow you to use the scan mesh as a smart reference to build your model in ways that traditional CADs don't allow. So you will find that a growing number of CADs are introducing some kind of scan to CAD support, but you'll also find that the functional differences between those, afterthought additions and dedicated RE products like Geomagic can be pretty dramatic, and that's kind of what you'd expect considering their exclusive focus and the 25 plus years behind their algorithms. So if you have some experience, but your only frame of reference is whatever reverse engineering module came in your CAD package, or if you've been trying to do it without one, you'll be impressed by what Geomagic can do. The other type of model we're talking about is a surface model like this one here. They're created from a network of patches. You've probably seen STEP and IGES files that look like this at some point, right? So these models don't have a feature tree, and they don't allow you to make edits just by, say, changing a face location by typing in a new dimension. But they can be cut and merged with other CAD objects, and they're useful in a lot of situations. This makes an exact copy. So unlike the method we previously discussed, you won't as easily be able to ignore imperfections and model according to design intent. But the main advantage here is that unlike feature-based models, these models right here can usually be generated automatically with just a few clicks. So if these are good enough for your application, they can save you a lot of time. So with those basics covered, let's go ahead and scan something. So I'm just gonna start scanning this brake pad. I'm gonna turn it in a few different directions. If anyone is wondering, as you see it turning, I have this on a little turntable. It's just a Lazy Susan that I bought on Amazon for $9. You might also notice there are no target stickers on here. Some of you might be familiar with other brands or older handheld scanners where you got to put stickers all over the objects, and that's not always necessary depending on the type of scanner you have. So there's one, but I want the whole thing, so I'm going to turn it upside down. I'm going to scan it from a few different angles, and then we'll connect the scans together. There's the data from the first one. It never looks like much until it's processed, but the end result will be pretty cool. Now, you might be noticing that green histogram there on my left. That's just my standoff distance. That's the basic distance that I want to be from the object. As you can see, I can move in and out. You know, I have a lot of wiggle room, but if I go, you know, extreme, if I go too far in either direction, the scanner won't be able to track. It'll lose focus. And that's common to pretty much all 3D scanners, is that there's some kind of focal point. I'm going to go a little overboard on this thing and do 4 scans of it that will connect together. For reverse engineering purposes, it really doesn't matter if you have a few holes in your mesh. One of the biggest rookie mistakes is trying to get too complete of a scan when you really don't need it for what you're doing. So, you know, we certainly don't want to just go crazy with scanning when we don't need to. But I want to produce a good looking scan for you guys, so I'll go just a little bit overboard on it. All right, there's the third one and the final one. And of course, we're going to have a QA session after this, so I'm sure everyone has questions. And we'll have plenty of time for them, I think. We will have to cut this off sharply at noon, but we have plenty of time to meet with people privately or chat with you through email, launch a private GoToMeeting and show you whatever you want to see. So if it turns out that we don't have time to answer every question, don't worry too much about it. All right, let's call that good with our scanning. So we're done with that part. That was pretty painless. So what we were seeing in real time, those were just lightweight previews. The final data is going to look more detailed and sharper than that, and it'll be more accurate. These are just something we use as kind of a visual aid. So I'm going to go into Tools. It's starting to remove the bases. That's because I had this option called Automatic Base Removal turned on, where it tells me to point the scanner at the base, and during that time, it's looking for planar faces. And when it identifies a planar face, like something flat like a table, it flashes a grid, and that's when you know it's identified the base. And from there, you can start scanning, and that base will automatically be removed during this stage. You don't have to have this option enabled, but you know, there are some things like a very symmetrical gear or something where I might want to use the base colors. Like you see how I have all these colors on my base here. If a gear's very symmetrical, how would I tell one side of the gear from another if I only scanned half of it? And so that can come in handy. So sometimes I might prefer to use that, and then at a time of my choosing, I'll come in here to the editor and I'll use this feature called Cutout Plane. And I can just highlight stuff, and it identifies a planar face based on that, just like base removal. Make sure I get all the way around it. There we go. And you'll notice that these scans are, you know, pretty noisy. That's going to be cleaned up with something called outlier removal. So it's hard to believe at this point that something that looks this messy could turn into a really nice model, but you'll be surprised in the end. So when we have the bases removed, we'll just go to align them. There's an auto-align feature here that works practically all the time, but on simple stuff like this, it can actually sometimes be easier just to align things yourself, because recognizing geometry is something that computers try hard at, but it's something that human beings are obscenely good at. So I can actually align these so fast that sometimes with simple objects, it's not even worth it. Oops, I did this one wrong. So I'll just say this is approximately right there, and this is somewhere around there, and this is somewhere around there. And as you can see, I'm not getting real exact because the computer will do the rest for me. Same thing. And if those colors are messing me up before they're processed, they don't look like much. So maybe this view is a little easier to look at for me. Same thing. Align those. And the last one. All right. So they're aligned, but it's still pretty ugly. So let's clean it up. First one I'm going to do is this global registration. So if you guys look over here in the top right corner, there are these numbers, 222, 226. Those are the numbers of individual frames in each scan. And right now it's shuffling every one of those all around until they're perfectly superimposed on each other. These are pretty much in the order I need to do them. The next one I'm going to do is outlier removal. This scanner is actually high enough resolution that it can pick up things like dust motes floating through the air. So this step here is just making some educated guesses as to what belongs and what doesn't. I got a warning here. It's telling me that, hey, there's one of these frames that I just could not reconcile with the rest of the data. Maybe it was, your hand moving through the frame or a cord or something like that. But in any case, it didn't think that it made a lot of sense. And so it's asking me if I want to get rid of it. I can also just get rid of things that I think are a little too high for my application and kind of narrow it down to just the best quality data that I have. And at the end of it all, I do a sharp fusion. And the fusion is basically just making an STL file. It's kind of like we have a point cloud right now and we're connecting the dots, to put it simply. So this is usually the most time-consuming step. This is probably going to take a solid 2 minutes or so. And this will be the last step. The product that this produces is what I'm going to hand off to Sean, and that's what he's going to model from. So this is just going to be an STL file. It's the same format that pretty much all reverse engineering is based on, the same format that's used in 3D printing. Pretty much all major CADs can import and export one. So here it is. You can see that modeled surface just like on the real one. And the roughness of the fibers and everything. So there it is. That's it for scanning. That was pretty much every process. And these basic steps apply to pretty much any object you can scan, with the exception of if we wanted to add color, which we can do, but obviously that's not very relevant for engineering. So we're not going to do that today. So I'm going to save this out and hand it off to Sean Parker.
Sounds good. Well, thank you very much for having me in here, and I'll get started by sharing my screen with you. What we're going to do is take the file that Ian saved out, that BreakPad STL file, and bring it into our Geomagic for SolidWorks plugin. Today I'm going to be running this in SolidWorks 2015. We're compatible all the way back to 2011, maybe 2010, I can't remember. But with at least the last several releases of SolidWorks, and then of course we'll continue to add functionality and so on and so forth in future releases of SolidWorks. So I'll be using 2015 today. Having received that file, essentially what I'm going to do is start a new part file just like you would in any other project inside of SolidWorks here. And I've enabled my add-in. So just to take a look here real quick. Geomagic for SolidWorks is a separate add-in. It functions just like any other inside of SolidWorks environment. It is licensed separately from SolidWorks, but we can match the SolidWorks license style. So if you have a network or a floating license there, we actually use the same license server as SolidWorks, just like there. And when I enable that plugin, I can see that I get a brand new tab show up in my user interface inside of SolidWorks. And it's a left to right tab filled with tools that are kind of the greatest hits collection of Geomagic processing tools that we've been developing for 25, 30 years now. So if you're not familiar with who Geomagic is, we are the software branch of 3D Systems. And we are kind of the composite of a number of different companies that were independent until a couple of years ago. Two of whom were known as Geomagic and Rapidform, and they were two of the leaders in industrial scan data processing and collection tools. We've partnered with Dassault and SolidWorks recently to bring a large number of those tool sets into the SolidWorks environment. I don't know. Apparently we're having issues with audio. Is that the case? I'm going to just ask a quick question because apparently I was having some audio issues. Are they still persisting? Phone call, I was having some issues. Can I get confirmation that people can hear me now that I'm on a computer microphone? Is this any better? All right, perfect. So I apologize for those issues. Sometimes we can have these little technical problems here, but I'll kind of restart my spiel here, and hopefully the audio continues to be in good quality. Please do let me know via the chat function if you cannot hear me for the remainder of my talk. So again, my name is Sean Parker. I work with 3D Systems and Geomagic. And my portion of the webinar today will be taking that STL file that Ian saved out and bringing it into our plugin, which is Geomagic for SolidWorks. And Geomagic for SolidWorks, as you saw me show up on the screen a couple of seconds ago, is a add-in for SolidWorks. We can license it the same way that SolidWorks licensed their products in using the same Flexera licensing system. But it is a separate license. So once you have access to that, you have access to this tab inside of the SolidWorks environment. And we're compatible back to at least SolidWorks 2011 and currently compatible with the new version of 2017 and 2018 as well. But I'll be in 2015 today for this demo. And as you can see, when we open up the plugin inside of SolidWorks, we exist as a separate tab, just as anything else kind of would inside of SolidWorks here. We have a left to right workflow that is essentially the greatest hits collection of the tools that Geomagic has been developing for scan data processing and reverse engineering since the mid-90s. So we have a lot of pedigree in this market, and we've recently partnered with Dassault within the last 18 months or so to bring the most commonly used features and tool sets from our standalone 3D scan data processing applications into the SOLIDWORKS environment. So over the next 30 minutes or so, I'll kind of show you what that looks like. Now, I can start in one of two places here. I can either import scan data from scanners like Ian's RTech there, or there are a number of devices that I can connect to and scan with automatically. The handheld systems, though, they don't function inside of SOLIDWORKS like the RTech does, and their software is going to be a lot faster at cleaning up and optimizing and meshing and basically that whole process that Ian showed a minute ago. So once we have that file completed, what I'll do is I'll just find it that I downloaded. He just sent it to me here, and open it up inside of SOLIDWORKS. And you'll notice that I'm not doing this in a way, if you are familiar with Scan to 3D, the SOLIDWORKS plugin, or actually the SOLIDWORKS add-in for premium users. I'm actually importing this in a separate form than just kind of opening that STL file into SOLIDWORKS. This gives me the ability to use some tools that we kind of learned from Photoshop and even MS Paint to edit the scan if we need to. If I right-click that feature and go into my edit mode here, I can see the number of triangles that it kicked out, so about 200,000 triangles, which is already a detuned version of the max resolution then that Ian Scanner can pick up. And I can also see the size of the bounding box here just to make sure that my units are correct. So we've got about a 5-inch long brake pad. If I go into my context mode with the right mouse button here, I can see that I've got several selection tools and several selection options that will allow me to either select via a box, a kind of freehand shape, a lasso tool, and a paintbrush. And then also I can select all the way through the object if I'm trying to just clean up a large portion of scan data, and use my delete key to get rid of that, or I can invert this here. But that work has already been performed for me inside of the RTech Studio software. And I should mention, if those of you that were watching Ian's demonstration thought that the scan data cleanup and processing steps looked a little bit daunting if you have no experience with the scanner, there is actually a kind of automated or semi-automated version of that. So you don't have to remember the process yourself. You can just have the software walk you through the important components to get this type of STL file here. So this has already been cleaned up. The table's gone. The files are merged. I'll go ahead and exit my scan data cleanup tool here, and we'll get into sort of the modeling. Now, since this is a handheld scanner, even though the part was sort of mounted on that turntable, that Lazy Susan that we saw before, the handheld scanners really don't have a great way to orient their scans as they're incoming to the world coordinate system. So if I show my front, top, right, and origin plane here, I can see that maybe the part does sit near the origin, but none of my system planes have any sort of a match to anything relevant on the scan data. This is a part that has some symmetry. It also has some nice planar features, and I would really like to be able to put my origin in a location that references some of those. So getting back to the tab here, I've got some groups that we're not going to use. For example, if I have multiple scans, I can align them, very similar to the way that Ian did before. If I have point clouds, I can do some editing tools to them, and I also have a large number of edit tools here to fill holes and smooth and repair and do certain things to that extent. To the file once I get it in here. And this is a very small file as far as 3D scans are concerned. 200,000 triangles is actually relatively small. But if I wanted to make it smaller, for example, I could go into my Simplify tool, and I'm going to turn on my triangle display here so you can see the size of the individual scan components on this part. It's relatively high density. If I wanted to knock that down, I could certainly do that. And we'll do a curvature-based intelligence decimation. Or, for those of you that don't want to have such a mouthful of a term, basically, a smart simplify tool, where I make larger triangles in the areas that I have flatter curvature on my scan data and still smaller triangles to convey the high level of detail that the sharper corners have here. What I can also do with this, I'll turn my edges back off here so I can see this from the outside. If I do want to do some smoothing, I can smooth my file, get rid of some of the roughness. Maybe I don't want the texture of the ceramic or whatever the material the brake pad is made out of. I can certainly run a smoothing operation here and give myself a little bit more of an aesthetically pleasing part. What I can also do is check the part for any potential issues. Maybe I've got a triangle that is floating in space, or I've got a spiky vertex from my mesh or something like that. And I can have the software automatically correct those issues for me. And the reason that we do this, not necessarily is for a rendering concern, and it's certainly not for a mechanical reverse engineering concern, but the first thing that I'm going to do from a scan data modeling consideration is actually do the second of the two workflows that Ian was talking about earlier, where we just say, here's my scan data. It's a series of triangles in this STL format. Let's just wrap them in a series of NURB surfaces and do a very quick and very accurate conversion to CAD so that I can design a new component around this. But before we get into that, again, I do want to recognize again that the origin is not in a place that I would like it to be when I'm designing my tooling around this or putting this into an assembly, whatever it might be. So I'm going to extract some reference geometries very quickly here. And the first thing that I'm going to do is extract a symmetry plane from the center of this part. So I'm going to manually draw a line of symmetry close to where I think it should be. And of course, my angle is quite wrong here, but that's just my initial guess plane. And when I hit preview, it's going to best fit a true symmetry plane to the center line of my part, and when I hit OK, I get a SolidWorks plane. I'll do the same thing in a slightly different fashion here by using the reference plane tool to find the top surface of this part. And what I'll do is I'll use my Smart Selection tool, which allows me to very quickly select mesh triangles based on their curvature just by dragging. So if I get very close to the part, kind of drag down here, I'm selecting a very small area of the scan. As I increase my curvature threshold, I will be able to select pretty much that entire top surface there very, very easily, and then best fit a plane to that. Now, if I want to put my origin anywhere specifically, you know, I'll have to find a third thing on this part that sort of makes sense. And maybe what I would like to do is extract, you know, a cylinder from this area here, which I know is roughly cylindrical, or maybe I would do it on the front of this part here, and I can find the axis. Maybe that's a little bit too large of radius here. We'll try that again. That's a little bit better there. So that's going to put the origin, maybe not necessarily attached to my part, but in a frame of reference that I can use this. So I've got an axis there that intersects this bottom plane. And so I'll go back to my SolidWorks Features tab here, grab a regular reference point and say intersect this plane with this top surface that I selected, and that is going to be my point of origin. So getting back into the Geomagic for SolidWorks tab here, I've essentially set up my coordinate system where my z-axis can be defined, or my xy plane can be defined off of this plane here. Maybe my x-axis can be defined off of that, and my 0, 0, 0 point can be out in space. And the Orient Mesh tool will allow me to use those reference geometries and say my origin here is going to be that point. My z-axis is going to be this plane, and then we'll say again my y-axis is this plane here. And I can see with this little colored axis indicator the orientation of any of those axes. If I need to flip something like my z, get that pointing positive up, I can select that there. And then I'm going to just hide all of these reference geometries. I don't need them anymore. My origin, my front, top, and right plane are now located properly. And if I use my default views here, my top, my bottom, my front, back, left, right, that sort of thing, you can see that my scan has been translated in space. And now it's time to go through the reverse engineering process. Again, there are two methods that we can use to generate CAD from this scan data. The first of which is the automated approach, which just allows me to tell the software that I want it to build surfaces from this scan, or extract surfaces from this scan data. I can tell it roughly what type of object it is and how tightly I would like this CAD model to fit the scan data. And then I'll let it do the work itself. Now, I'm not going to have a lot of editable control over the file that I get here, but if I just want a CAD representation that is very, very accurate to the scan data that we generated, maybe I'm doing a mold design, for example, around a toy, and I just need something to Boolean out of my mold tool, that is a way to do this. So this is kind of the longest step, but it is all completely automated here. It'll take about maybe another 30 seconds or so to finish building this CAD. And then I'll show you a couple quick things that we can do with this CAD model once we have it, you know, kind of extracted from that scan data. Just another second or two here. All right, very good. What I'll do is I'll hide my scan, and we can see the model that we have underneath extracted from it. Okay, and this is a series of NURBS patches. If I hover over this, or if I use my edge display here, I can see that those patches have been fit roughly to the contours of the part, but really there's not much that is editable about this file. The only thing that's really editable is just changing it out with another CAD file. So that's still okay though. If I took one of these planes here, for example, this guy, and I did a sketch on top of it, I'm just going to create a very basic body that we can remove this CAD from. So I'll just grab a rectangle tool here very, very quickly, exit my sketch and extrude. I'm going to be extruding that in the opposite direction here. And I'm going to just offset the starting point of that extrude. I don't think I can. So if I use my Boolean tool, or what they call the combine tool, if I can find it here, or the intersect tool. Actually, I'm sorry, it is the combine tool. Tools. Oh, I think I merged this result. That's the problem here. I created a single body from all of that, so I want to keep these guys as separate bodies before I go into my next step here. That'll do it. Combine tool will allow me to subtract the body that I auto surfaced there from this body that I've got, and I'll keep this, and I can see that cavity there. Now I did my extrusion from probably a bad plane, so I should probably redo that. But internally, at least, the geometry will match. So if you can imagine creating like an injection mold or something from an object, this is a great way to do it, where I don't have to, especially if it's a toy, if it's an organic shape, it's very difficult to model with the traditional extrude, loft, sweep, sketch-based modeling techniques that you would use for a lot of mechanical parts inside of SolidWorks. This is a very good way to just get a CAD file from anything, essentially, and then design new tooling around it. So that's great. I am going to delete this, though, so I can kind of go back and model this part in a more mechanical workflow that's appropriate to the type of object that it is, essentially. So just delete all of those objects here. I'll show my brake pad again. And what I'll recognize is there's a few features on here that could be, you know, easily modeled with a sketch and extrude, right? That's the kind of main body here. I could extrude, cut out this sort of triangular shape down below, and then I could extrude and merge this top surface here. The rest of this we could add in as a second sketch. And again, this is a very basic part, so not a ton of complexity, but you know, should be pretty easy to extract some of these main features here. I'll go ahead and use a extrude tool, this extract extrusion tool, and I'll select the first body that I'd like to generate here. And I'm just selecting the areas, basically the walls or the things that will become the sketch of my extrusion. And I'm going to let my extrude profile get automatically generated from it. Now this is a pretty ugly profile that's generating here. I should be able to optimize this later on. And sometimes that selection mode is not the easiest way to do it, so I'll just take over and take a manual slice from this. Instead of using my sort of wizard selection tool, I'll just say select through and take a small chunk here. And that's much better. I can constrain that sketch to be either on or normal to an existing plane. So I'll use my front plane here to constrain that. And I can see in a little bit of low resolution, or I can see in a little bit minor detail here, the blue outline of what that sketch will become. So when I build my extrusion, I get an instant solid body, and I get it in an editable fashion that I can go back in and edit this sketch. This is a native SolidWorks sketch now with lines and arcs, and if I hide my scan data, I can see the fitting that I did performed was a little bit on the loose side. So I've got a dark blue cross section here that I just fixed. This is actually where my scan data intersected that reference plane that I selected to put my scan data on. And then to varying degrees of complexity, the plugin, Geomagic for SolidWorks, will fit line and arc sections to that area. But these are editable if I'd like to go in and maybe change a couple of things here to make that a little bit more accurate, kind of square this edge off. I certainly have the ability to just fit a single line to that area and then corner trim that with its neighbors to maybe reduce the complexity a little bit. And when I save that out, the extrude will update to have a square in that area. While I'm doing this, I do want to take a look at how closely that feature that I just fit matches the scan data that it was extracted from. So if I go to my Deviation Analysis tool here, I'll select the body that I want to do a comparison with, and I'll keep this relatively low resolution so that it generates the preview very, very quickly. What this tool will tell me is two things. First of all, the feature that I did fit here, it'll give me a accuracy statement based on the editable sort of color map on the side here, and saying that everything within this green color is within about 11 or 12 down. I'll see that on the bottom that's all right as well. It'll also show me areas that have been yet to be modeled. So that dark blue area here, this sort of lighter blue area on the top there, tell me that I still need to add some features in here. So we'll go ahead and do that right now. I'll do the extract extrusion tool again, and I'll make another selection, that automatic selection tool, to build my next extrude profile from this whole outer shape. And I'm not doing a bang up job of selecting all these radius corners here, but it does allow me to optimize this profile, and it will find more of those radius areas here, or I can go back in and manually select them. Or of course I could just model those radii as fillets later on, rather than trying to incorporate them into my sketch profile. So I'll go ahead and join this new body that I'm building with my existing body. And if I get to a feature where I maybe cannot use one of these extract extrusion or revolution or even a primitive geometry tool like my cylinder tool, I always have manual override. And what that's going to look like is if I find, let's see, probably this plane. Yeah, we'll use that plane. And I'm going to focus on this tiny little feature down here. I can always manually override and extract a cross section from an existing piece of reference geometry. And of course, this is really far away, so I'll drag that into my part. And what I'll see here is a preview, and of course I've got some geometry in the way, the CAD model and the scan data. So maybe I'll do this again and hide my solid body here at least. Give myself a little bit more of a fighting chance to be able to see this cross section as it's being extracted. So I'll do this again from this plane, offset that into the part a little ways. And this is essentially what the software was doing when I was using the automated modes before. But now, you know, I can just take this cross section at any point offset from this main plane here and convert that either into polylines or into lines and arcs or into a spline. And in this case, I'm only interested in this small feature in here. So I can actually say, just ignore everything else, but give me a cross section of this smaller area here, and it will build. You can see the black lines are starting to appear. Oops, went a little bit overboard there, but it'll build me a cross section only on the area that I'm trying to focus on. And in this case, you know, we'll kind of ignore this whole thing and build this just as reference geometry, so that I can take this sketch here and just copy the areas that I'm interested in. I'll completely ignore all of the rest of that polyline, go in normal to my part, and then I'll just basically trace using my regular SOLIDWORKS sketching tools the area that I care about. Maybe add a fillet between these two sections. And I'm getting the signal from Ian that we want to make sure that we get enough time for Q&A afterwards. So I'll go ahead and actually end the demonstration portion of this session there. But that was a couple of the basic features that Geomagic for SOLIDWORKS has. I'm glad that you know, I was able to show as much as I could here, but there certainly is a lot of other, or there are a lot of other options for creating CAD geometry from the scan data. This is the two kind of the most basic approaches though. With that, what I'll do is I'll go ahead and open the floor up to questions. If you have one, you can certainly type it in the comments field here, and Ian or I will read it off and hopefully get that answered for you as well. If we cannot get to your questions, certainly we'll be following up via email, and we can make a more custom session to you via a web demo in the future. But with that, go ahead, Ian. I'll hand the reins back over to you. And thank you very much for joining, everybody.
Thanks a lot, Sean.
Yeah. My pleasure.